Mankind has employed nanotechnology for millennia, with applications ranging from Damascus blades to stained glass windows to nanofilms, and it is only in the last 40 years that we've really begun to understand the properties of nanoparticles and the magnificent colors they create. From the 16th to 18th century, medieval artisans accidentally discovered the colorful properties of nanoparticles, without understanding the science behind them. For example, they realized that adding gold chloride to molten glass tinted it red, and adding silver nitrate tinted it yellow. The color of a nanoparticle solution is related to nanoprism sizes and shapes, and it was on this that our research focused, using the same materials as hundreds of years ago, like silver nitrate.
Nanoparticles are those with a size between 1 to 100 nanometers and were first discovered by Michael Faraday in 1857. Nanoparticles tend to have very different properties to bulk materials due to their vastly smaller size, usually on almost a quantum scale. This is primarily due to the fact that as a particle gets smaller, the fraction of atoms within that particle that are on the surface increases, which means that things typically get a lot more reactive as they get smaller, leading to the different properties of nanoparticles.
To investigate the optical properties of nanoparticles, we prepared solutions of different size silver nanoprisms. We used silver nitrate as a source of silver ions, and added hydrogen peroxide as an oxidant, sodium borohydride as a reductant, and sodium citrate as a stabilizer. To alter the sizes of the nanoprisms, we also added varying amounts of potassium bromide, KBr, which inhibits the growth of the nanoparticles as bromide ions bind to the silver surface. As seen in the video, the color of the solution went from blue to yellow with increasing concentration of KBr, potassium bromide, which corresponds to smaller nanoparticles. Solutions with 15, 30, 45, and 55 microliters of KBr resulted in blue, wine-colored, dark yellow, and lighter yellow solutions respectively as shown in the picture. Using UV spectroscopy, we found that a blue, 10 microliter KBr nanoprism sample had maximum absorption at 678 nanometers, its complementary color red.
The whole idea of surface plasmon resonance begins with a plasmon, so we have to ask ourselves, what is a plasmon? If we think about where the word plasma comes from, plasma is a gas of charged particles. Similarly, a plasmon has electrons as a gas of charged particles responding to an electric field. Light is an oscillating electric field, and when this oscillating field penetrates sufficiently deep into a metal, which is very possible in nanoparticles because they're really, really small, the electron cloud responds by moving back and forth because of the electrical interactions with the field. Depending on how long the electrons take to slosh back and forth in the particle, it can be in resonance with the oscillations of light that is hitting this nanoparticle. And when that happens, we get a surface plasmon resonance. This causes a strong absorbance at the specific wavelengths of light where the electrons of the nanoparticle are forced into oscillation due to this strong coupling between the electron cloud and the wavelength of light shining on it. This adsorption results in the bright colors we see in our nanoparticle solutions. When light of a certain wavelength is adsorbed, for example orange wavelengths, the solution appears to be the complementary color blue. Thus, in our experiment, as some of our nanoparticle solutions looked blue, that means that orange wavelengths of light were absorbed. The shape and size of nanoparticles can affect the wavelength of light at which surface plasmon resonance occurs. This means that different sized and shaped nanoprisms will absorb different wavelengths of light, thus appearing as different colored solutions. This difference in absorption allows us to estimate the nanoparticle size and shape from the absorption spectra. The larger the nanoparticle, the larger the wavelength of absorption, so the solution will appear a color of higher wavelength. For example, nanoparticles around 100 nanometers in size will absorb colors on the red end of the spectrum, making the solution appear blue-green. Smaller sized particles correspond to smaller wavelengths of absorption, such as blue-greens, resulting in a red appearance. This can be observed in our experiment, where potassium bromide acts as a capping agent. The more that's added, the smaller the nanoparticles are. The smaller the wavelengths absorbed, resulting in a spectrum of blue to yellow or red as more potassium bromide was added, and the nanoparticles progressed from large to small.
Hopefully you all now have a better understanding of nanoparticles and how they contribute to the color of a stained glass window through their varying sizes and shapes. This principle, applied in the 16th century, is now understood, and it is through understanding that future applications can be developed.